continue our discussion on this topic that we had started yesterday, error-free communication over noisy channels. Essentially the concept of channel capacity, how it comes into the picture, and how, as Shannon told us, it's possible to think of transmitting information at a finite non-zero rate but within certain limits and still guaranteeing error-free communication, right? At least in theory. In practice, of course, things may be different, but at least in theory, how it is possible to think of a result like that. And let's go over the justification. And if you remember, I had started about this aspect by considering the role of redundancy in error-free communication yesterday, right? The crucial thing that we had tried to say was that it is by the use of by the transmission of redundant information along with information that you actually want to transmit that it is possible to think of error-free communication at all. How exactly, we will still talk about that, but the concept of channel capacity, in fact, as we will see today and as I discussed yesterday, is it tells us that if you are transmitting symbols which contain a certain amount of information, how much of that information can be information of interest to the user and how much of it must be redundant information, right, which is of no direct interest to the user. For example, if every symbol of a if your channel capacity is 0.4, that was the example we were taking. If your channel capacity has a value of 0.4, right, that means whatever amount of information is being conveyed by every symbol of your transmission, whether it is 1 bit or more bits, only 0.4, a fraction of 0.4 of that can be useful information. The rest of it has to be redundant information. If you are transmitting 1 bit per symbol, then 0.4 bit has to be useful and 0.6 bits has to be redundant. That is the implication or meaning of channel capacity when it is to be taken as, when it is taken as a number less than unity, right. Now to see how such a result comes about, if you remember, we were discussing this example of excuse me, repeated transmission of a bit for introducing redundancy, right. For example, 0 followed by is transmitted as repeated transmission of 3 zeros, 1 as repeated transmission of 3 ones, and we could get a geometrical picture for the operation here by thinking that these two code words are these two vertices in this Hamming cube, right, and we could do a similar extension of this idea, maybe 5 repetitions or 7 repetitions, and then correspondingly we are thinking of a 7-dimensional Hamming space or a 5-dimensional Hamming space, right, and the cube is the hypercube that you have to consider is in that particular space. But the important thing to note is that because we have chosen code words a bit carefully, it is because we have chosen code words a bit carefully, we are able to get features of error correction in this scheme of things, right. The philosophy of choice is that for every code word that you select, for every vertex that you select as a code word, basically I have chosen this vertex and this vertex as code words. For every vertex that you select as a code word, you have to leave out all neighboring vertices or a few neighboring vertices unassigned as code words. They should not be assigned as code words. They should not be chosen as code words. In this case, of course, the maximum we can do is leave these vertices unassigned if we want to choose at least 2. In the case of 5 repetitions, we can leave out more vertices unassigned and correct up to 2 errors. For example, we could leave out all vertices which lie on a Hamming sphere of radius 2 unassigned in a 5-dimensional situation, right, and therefore we could get a double error correction capability in that situation. Okay. Now, as you keep on increasing the number of repetitions, it's quite obvious that the distance between these chosen code words will keep on increasing, and in the limit we'll get a situation where there is very small probability of confusing one for the other, right? But do you think that justifies channel capacity argument? No, because simultaneously what is the effective information rate that you are going to get? Again 0, again 0, right? So although we have introduced redundancy and we were hoping to get the channel capacity kind of situation, that is finite information rate transmission without errors, we don't see that kind of thing happening here, right? The reason why it is not happening is because our manner of introducing redundancy is not really very nice. You appreciate that? Excuse me for a second. Okay, because what we are doing is we are introducing a lot of redundant bits just to check on one bit whether it is going in error or not, right? And that's not a good thing to do. The better thing to do would be take a group of bits and have a common set of redundant bits which will check on that complete group of bits, rather than just designing system to guard against errors which may be on single bit basis, right? That's not a good thing to do. It's nice to give this argument which is given in the book also. Suppose you have basically what are these bits doing? Guarding against errors that might take place on the channel. If the errors take place in the channel, you will be able to correct it, right? So it's some kind of a guarding phenomenon, guarding mechanism. Suppose there is a street or a neighborhood in which there are a lot of cases of burglaries and dacoities. There are two ways of tackling the problem. One way is each one of you or each one of the residents hires his own guard. Not a very practical thing to do. A better thing to do would be to get together and hire one or more common guards to take care of the problem, right? It's the same kind of situation here. So instead of trying to introduce redundancy to correctly transmit a single bit or a single digit, we would like to introduce a set of check digits or redundant bits to guard against errors in a group of bits of information together. That may be more efficient way of doing things rather than this way of doing things. Okay, so now let's therefore try to do things in a slightly different way, that is add redundancy in a slightly different way. We'll take a group of bits and I'll introduce some notation for that. Let alpha be the binary information rate. That is the rate at which input information bits are coming along. Okay, and let me accumulate these incoming information bits over some period of time to get a group of information bits, right? Let's say this time is t seconds. So in t seconds, how many bits I will accumulate? Alpha t, right? And these are the number of information digits in t seconds. Okay, and what I'll do is for every group of alpha t information digits that are coming along, I'll transmit a group of beta t digits actually on the channel. That is, my code words will have length beta t, not alpha t. So basically what I'm going to do is add a few extra bits equal to beta minus alpha times t, which will serve as the redundant information, or what is also called check digits. Okay, so these are the number of what are called check digits, and these check digits constitute the redundant information that you are transmitting. yes, normally these are bits, but one can also have a more general scenario where one can talk of more abstract symbols. You can have non-binary value digits also, but for our discussion, let's assume that they are all bits. Okay. So there are beta t transmitted digits for every alpha t information bits. For every alpha t and information digits. Now let's look at things in that geometrical framework that we were talking about. What is the number of messages that we have to convey if you are conveying alpha t groups of bits together? How many different messages are of interest to us? We have a source which is emitting a group of alpha t information bits, right? What is the number of different messages this source can generate for us? 2 to the power alpha t, right? So number of messages which are of interest, which we may want to convey one time or the other, which are of length alpha t, is 2 to the power alpha t. And what is our code word size? What is the final length of the code word that we are transmitting? Beta t. So how many different sequences of that size we can have? 2 to the power beta t. So I'll say number of possible sequences. What is the physical significance of this 2 to the power beta t? These are the number of possible received sequences. Because although you may be transmitting only these 2 to the power alpha t sequences out of these 2 to the power beta t sequences, after corruption with noise, after degradation, you can receive practically any sequence theoretically, right? So number of possible received sequences of length beta t is 2 to the power beta t. Or we can also look upon this in a different way. Our final code word is of size beta t, right? So in that Hamming space that we are talking about, what kind of hypercube is defined by this length of code? It's a beta t dimensional Hamming space, and the number of vertices in this Hamming cube will be 2 to the power beta t, right? You can think of this in that way also. There are 2 to the power beta t vertices in the Hamming cube corresponding to the Hamming hypercube in the beta t dimensional space. Okay. So let me write that. You can also think of this as the number of vertices in the Hamming cube in the beta t dimensional hypercube. Fine? Agreed? Out of these 2 to the power beta t vertices in this hypercube, how many of them will you finally select as code words? 2 to the power alpha t, right? And of course, how you will choose those code words is a matter of designing the code. We are not at the moment going into that, right? We'll go a bit into that to take our argument to completion, but the important thing to appreciate here is that the fraction of vertices which will be used as code words, I'll call that fractional occupancy. Okay, so this term fractional occupancy essentially tells me what is the fraction of code words, what is the fraction of vertices which are being used as code words.
But code words is 2 ratio beta t.
No, 2 to the power beta t is the total number of vertices in that cube, right? Out of this, only 2 to the power alpha t are assigned as code words, right? Therefore, the fractional occupancy of code word vertices with respect to total number of vertices will be 2 to the power alpha t upon 2 to the power beta t, which you can write as 2 to the power minus beta minus alpha t. Okay, because beta minus alpha is positive, so I written it like that. And what is the rate of information reduction? What is the reduction factor in the transmission rate of information?
Alpha beta.
Alpha by beta. For every group of beta bits that you're actually transmitting, or beta t bits that you're actually transmitting, only alpha t of them is information bits, or information bits, right? So there is a reduction factor in the information rate involved. I shouldn't say transmission rate, I should say information rate, yes. Is alpha upon beta, which is going to be less than 1, right? You can think of this beta t bits as being one symbol of its source, right? Out of this beta t bits that is being conveyed by this one symbol, only the fraction alpha t, only the portion alpha t is really information number of bits, the rest is all redundant bits. So this is linked with our reduction that we talked about in connection with channel capacity, right? No, but as far as this argument is concerned, again it looks as if it is only enough to have beta slightly greater than alpha, right? And I can make this reduction factor very, very small, it may look like that, and get zero error probability. Why? Because as fractional occupancy becomes smaller and smaller, that means around each assigned code vertex I have a lot of unassigned vertices, right? The number of unassigned vertices is very large, and particularly as t is made to go to infinity, right? Does it? But there is something wrong here.
The time that we are waiting for
No, time waiting, at the moment let's not worry about time that we are waiting for, right? But in principle it seems that with almost very little reduction in information rate, alpha by beta nearly equal to unity, and just make beta slightly greater than alpha, this will become a positive quantity. And if it is a positive quantity, for a sufficiently large value of t, it should be possible to make this sufficiently small, right? And it may look as if there is no concept of a channel capacity in that case. That is, one should be able to transmit error. One should eventually be able to have error-free communication without any reduction in information rate. Practically any reduction in information rate. This is a faulty argument. There is still something missing in this picture, which we have to make sure. It is not enough to just have small fractional occupancy. That is a required fact. What is also important is the other fact that I pointed out in that picture that we discussed. We have to make sure that Hamming spheres of a certain radius must not overlap with each other. The code words should be assigned in such a way that they maintain a certain amount basic distance with respect to each other, right? When you just look at fractional occupancy, we don't get that insight. We're not bringing that insight into the consideration. Okay, so now we have to bring in that insight also into consideration. That is, the code words have to be appropriately placed with respect to each other, and it's not just that I can have a lot of unassigned vertices and my job is done. Okay, yes, please. That's right.
That means the sphere will be very large around that particular code number.
No, but you see, just by saying that fractional occupancy is small, we're not saying anything about relatively where they are placed with respect to each other, right? Maybe you are putting them all together and the rest are all unassigned, right? That's not a good thing to do.
How can you say that, suppose as you said the distance between the code numbers is enough and the sphere are not overlapping, and also the fractional occupancy is small.
Let me complete the argument, maybe you'll understand. Okay. Anyway, this does indicate, because 2 to the power minus beta minus alpha t tends to 0 as t tends to infinity, right? It does imply that there is a possibility of error-free communication. This conclusion is right. Okay, but we cannot say from this that any value of beta slightly greater than alpha is adequate, right? That is, the channel capacity cannot be 1. That we cannot. That argument, the argument for that is not yet complete. I mean, we cannot say what's the value of. The question, therefore, that we ask next is, yes, please.
Yes, so how to conclude this?
This comes from this fact that since the fractional occupancy can be made very small by simply increasing t,
But you still, t is still tending to infinity, like.
at least in theory, suppose I am waiting, I'm ready to wait for an infinite or sufficiently large amount of time. In theory, it seems possible. At the moment, we are only talking of a theoretical possibility, not a practical solution. Mind you, this is not a practical solution to doing things. We will not really do things in this particular way when we want to introduce redundancy. We will not wait for infinite time.
But even in the previous case, if you keep on introducing a lot of redundancies,
Yes.
then the probability of error keeps going down.
But simultaneously, the information rate was also coming down to 0. Because only, you understand? Because only one bit information was being conveyed by infinite number of bits. What is the effective information rate? 0. Right? Now we are not having that situation. We have a finite number of alpha t information bits, beta t code bits. Right? So our information rate is reduced only by a factor of alpha by beta. And I can choose beta just greater than alpha to make this positive so that this happens.
So is it same as the earlier case that we said, if we wait for a long time, we can encode it in such a way that
that's our source coding. Now we're talking of channel capacity. Don't mix up the two issues.
But that
We are
CS
discussing source coding there. Now we're discussing the transmission of information over a channel. The context is different, the arguments are totally different. Yes, in both cases infinite waiting was required, but in different contexts.
The earlier said we defined CS as HM by L. The HM in the entropy and L is the availability that we require.
That was just by way of telling you what CS means. At that stage we had not introduced any argument of T. Right? That was just trying to tell you the concept of the meaning of channel capacity. Right? Nothing else. That how much redundancy one has to introduce. At that stage I just wanted to give an example. But now I want to give a justification for where does this concept of channel capacity come in from. Okay?
This implies that, not the
Yeah,
other.
this implies that rather than the other way around. Right? Any other questions? Sachin? Fine. So this is agreed that as t tends to infinity, we at least have a possibility of error-free communication coming from the fact that the fractional occupancy of vertices is becoming very, very small. Okay. The question really now is, can we choose, is there some limit on alpha by beta, or can I choose alpha arbitrarily close to beta, or beta arbitrarily close to alpha except it should be slightly greater than alpha? Right? The answer is no. There has to be a limit on the minimum value of beta that you must have for a given value of alpha. Right? And therefore it implies that you must sacrifice a minimum amount of information rate in order to achieve this. Okay? And that brings in the concept of channel capacity. Channel capacity is precisely this concept, that alpha by beta has to be less than a number which is a fraction. Alpha by beta has to be equal to or less than a given fraction, which is not unity. Fraction, of course, is not unity. How does that come? So that is a question next. Is there any limit on alpha by beta? And the answer is yes, there is a limit. To understand that limit, let's return to our example of binary symmetric channel in the context of which we discussed things earlier. Right? Let's say that binary symmetric channel, remember what was a binary symmetric channel? Let's say it is associated with the parameter P sub E, which is the error probability. Right? So let P sub E be the digit error probability in a binary symmetric channel. Now we are transmitting a code word of length beta t, and we are assuming t sufficiently large. Alright, so we have a very large number of bits which we are transmitting. Out of this transmitted number of bits, how many of them on an average can be in error? If t is large and therefore beta t is large, beta t times p sub e, right? So you when you're transmitting a code word of size beta t, the number of digits which will be in error on an average in a sequence of length beta t will be equal to beta t times p sub e, particularly as t tends to infinity. Agreed? And this puts a restriction. That means, what does this mean? That the received sequence, you are transmitting a sequence of ones and zeros of length beta t. The received sequence will be different from the transmitted sequence in how many places? On an average, beta t pe places. It will be at a Hamming distance of beta t times pe from the transmitted sequence. Now, if I want to use the nearest neighbor rule, which was implied by that assignment that we discussed earlier, I must make sure that from this received sequence there is no other code word other than the one which I transmitted, which is at a Hamming distance of beta t pe from this received sequence. There should be only one code word, which is a transmitted code word, right, at this Hamming distance from the received code. What does that mean in turn? That means for every code word, for every vertex that you choose as a code word, you must leave all those vertices unassigned which are at a Hamming distance of beta t pe from it, because all those are candidate received sequences corresponding to that transmitted sequence. Is it clear?
Yes.
Let me write this down for those who have not appreciated my argument. This implies that I must leave.
So the point is that
Let me complete this, then we'll come back to your question. All vertices unoccupied within spheres of radius. What is the sphere's radius of the sphere? Beta t pe, p sub e. Around, I'll have to go to the next sheet. Have you copied this? Around each of the 2 to the power alpha t occupied vertices. Is that clear?
so from the received signal, it should not be like there should be only one coded vertex within the Hamming.
No, but what is the implication of that?
That is the tools.
The implication is, see, you are transmitting a particular code word which is a vertex. The received one could be any neighboring vertex within this neighborhood, right?
That will be decoded as a vertex.
Then and if you are within that, you will come back to your vertex, code vertex. If not, you will go to some other vertex.
Nearest vertex.
You will go to the nearest vertex, right? So you must assign vertices as code words in this manner. You must essentially pack spheres in this Hamming cube, right? How many spheres you have to pack? 2 to the power alpha t spheres, right? Each sphere must be of radius beta t, and all these 2 to the power alpha t spheres must not overlap with each other. Is it clear? Can I request no talking, please? That is, we must be able to pack 2 to the power alpha t non-overlapping spheres, each of radius beta t p e vis-a-vis into the Hamming space of beta t dimensions. Fine. Now, obviously, if you want to do this kind of packing, there has to be a certain relationship between alpha and beta. You cannot just choose beta slightly greater than alpha and hope to do this, right? That is, if you have a particular value of beta, alpha cannot be more than the number of spheres that you can pack will be limited of that radius, right? And therefore, there has to be a limit on, and the radius will depend on the value of p sub e, right? So, how many spheres you are able to pack, and therefore, what is the value of alpha that you have to have? What is the reduction in alpha or beta that you can have will depend on the kind of channel you have. You have a good channel, your radius is smaller, you can pack more spheres. Your channel capacity is larger, right? If you have a very poor channel in which your error probability is large, right? Your packing spheres have to be of larger radius, right? And your channel capacity comes down.
So this beta dp has to be integer value? We have Hamming distance relating to integers, or?
Well, that's secondary to the argument. We'll assume that we take the nearest integer. As t tends to infinity, how does it matter, right? In any case, it's a t tending to infinity kind of argument, so one doesn't have to worry about that smallest.
Beta dp is also valid for t tending to infinity, or is it generally valid?
Beta t?
P that we are saying.
Well, see, after all, if beta t is tending to infinity, beta t p also will be a sufficiently large number.
No, is it valid for only t approaching infinity, or it's valid for only any value of t?
This argument is all asymptotic arguments, right? Because again we are using the relative frequency definition of probability, which is again valid only as the number of trials becomes infinite, right? So that it's all asymptotic argument. That's why I'm saying this is only a theoretical argument, really. Therefore, you may well ask, what is the significance of this? But let's come to, I'll come to that in a minute. The important thing for you to appreciate right now is that this brings us to a limit on alpha by beta, and that limit is precisely the notion of channel capacity. Right? Do you all understand that now? The concept of channel capacity, where it comes from? But now we know that if our information rate is less than channel capacity, we can think of the possibility of error-free communication, right? Which is a new result for us. It was a real major breakthrough when it came, because this possibility was never thought of by communication engineers before that. So for a given beta, alpha cannot be increased beyond a certain limit. Without causing the spheres to overlap, and then the scheme will fail. Therefore, it implies that alpha by beta has to be less than some fraction, which is what you call C sub s, and that depends on the channel parameters.
So we had derived a formula for CS.
Depends on channel, noise, and signal, transmitted signal power, and things like that.
So we had given a expression for CS on basis of PE. Can we relate the two?
I'll just come to
The two arguments here.
No, these two arguments are slightly different things. This is just to justify the existence of a concept like channel capacity and what it means for us. The next job is, how do you calculate this channel capacity for various types of channels? So that's what I gave you. That formula was an example of the calculation of CS, right? That comes next. So at the moment, don't mix up the two. What are the practical difficulties with this approach, and what is the significance of this result? Practical difficulty is obvious, that it is an asymptotic argument. It cannot really be done in real life situation. So therefore, and it's very complex. This way of doing things. In that case, why it is important at all? I think I have given you enough reason for that. You all appreciate that it is still important, this idea, in spite of the fact that this does not give us a practical method of achieving this possibility, because we now have a benchmark. We know that we can achieve this much, but not beyond this. Right? It's a very major breakthrough for communication engineers from that point of view. Okay? It tells us there is an upper limit on the rate of error-free communication of information. Right? And that upper limit is given by the channel capacity. So it's really a benchmark for. As far as practicality is concerned, since this result came, coding theorists and modulation theorists and communication theorists have been basically working on trying to realize this dream that was shown at that time, that is this possibility. And we are in a very lucky age that we are now living in a situation where we are very close to this dream. That is, we have schemes of modulations, we have error correction and modulation schemes which allow us to achieve are very near to channel capacity, if not exactly channel capacity. Right? And this is the result of a continuous research effort over the last 3 decades. Right? Last 3 to 4 decades. And a number of breakthroughs have come within this decade also. Now, yes, any questions before I proceed further? No questions? Now, I don't have time to go through what I had planned to do. What I had planned to do after this for you was to take up channel capacity calculations for both discrete channels, discrete model channels, as well as for continuous channels. Right? If some of you are interested, and I hope you will be, we'll take that up in some of the special lectures which will take up after your majors. Right? Otherwise, for the moment, what I'll do for you is just give you formulas for channel capacity for these 2 classes of channels. One formula I have already given you for the discrete channel. 2 classes of channels, channels which are modeled as discrete channels, or channels which you will rather model as a continuous channel. By continuous, I mean you are not using a binary symmetric model. You are working with an analog channel in which you have a signal power and noise power, and you want to express channel capacity directly in terms of signal power and noise power rather than in terms of error probability. Right? These are the 2 ways you can go about doing things. One can evolve various kinds of working with channels, various kinds of models for the channels, and have a channel capacity formula for that and for that kind of situation that you want to work with. If you, for example, work with a binary symmetric model, we already know what is the result for CS. Right? I gave you the result last time. CS is equal to, maybe I can just repeat it. I think I have it somewhere. No. Maybe I'll just give you that result and discuss that briefly. Yes, it is 1 minus P sub E log of 1 by P sub E plus 1 minus P sub E log of 1 minus. Okay. I think I gave you this formula yesterday, right? P sub E. That's the error probability associated with the binary symmetric channel model. Yes. Okay. It will be, now since I am not going to derivation, I think I just give you this formula, because derivation requires at least one complete lecture on that, which I have to skip. Now it will be useful at this stage just to plot this formula as a function of P sub E. right? It will be instructive to do that. If I just plot C sub S versus P sub E, what kind of curve you are likely to get? Can you make a guess? At P equal to 0, well, it's 1 and becomes 1 again. It's very interesting, and you might be surprised to start with, isn't it?
So if it is probably error is 1, then also we know that bits are always going to be flipped.
Correct. Okay. So really speaking, the worst channel is 1 corresponding to an error probability of 0.5, right? Of course, this is just an academic argument, because we don't normally communicate over channels with such large error probabilities, right? Our typical error probabilities are the order of 1 in 10,000 or 1 in 1 million, right? Not 0.5, but this is just purely an academic argument. The second point to remember, which I pointed out last time, is how do you relate this conceptual channel capacity, which is a fraction, with channel capacity which is usually given in bits per second, right? Remember the argument? That is going to be dependent on what is the rate at which you can transmit symbols on a channel, right? From other considerations. From other considerations, we know that for a band limited channel, the number of symbols we can transmit is a certain basic value, whatever it is. It may be 2B or it may be something else from some other considerations. Then your absolute value of channel capacity will be that factor K multiplied by C sub S bits per second, right? K can be 2B for band limited channels, or it could be something else from other considerations, right? Because this 2B is also after all a upper limit. Remember, you may be able to transmit only less than that because you are using excessive bandwidth. You are using Nyquist pulse shapes. K depends on other considerations, right? For example, bandwidth, and for example, the kind of pulse shape that you are going to use to transmit your things. So K is basically the number of symbols you end up using from other considerations. Being transmitted per second. Now, you may be also interested to know whether one can express the channel capacity of a channel without regard to a particular digital implementation, because this way of looking at things implies that you have a digital communication system for which an error probability is defined, and then you are going to use that error probability in this calculation, right? This is the implication of this use of the binary symmetric channel model, right? But suppose, after all, what does P sub E depend on? It depends on signal to noise ratio, and natural question is, can we express the channel capacity directly in terms of that signal to noise ratio, right? It's a very reasonable question, and the answer is, of course, again yes. I would have done it again if we had time. It was on my agenda, but I'll just give you the result. The result for continuous channels is as follows. But both these results, and particularly this one, which I'm going to give you now, are very fundamental results, and you must know them. And that is, C sub S will be log to the base 2 of 1 plus S by n. Of course, everywhere it is assumed that we are working with Gaussian channels. I think there is a factor of 2 also. No, the factor of 2 is not there. Okay, and of course the corresponding band limited channel will imply that you also put the 2B there. So in terms of, this is as a fraction, and this is in terms of bits per second, absolute value. This is a very famous Shannon formula for channel capacity of continuous channels. Let's take a typical example. Over telephone lines, your typical signal to noise ratio that you may have may be of the order of 30 to 40 dBs, right? and bandwidth is of the order of, let's say, 3 to 4 kilohertz, right? What will be the channel capacity like? Can you make a quick sample calculation?
Bandwidth is
Let's say 4 kilohertz. So this is 4 into 4000 into 2 into log 2 of, let's say, 30 to 40 dB means about, let's say 30 dB, right? 30 dB will be how much? A ratio of 1000. Power ratio of 1000 will be 30 dB, right? So this is about 1000. 1000 log 2 of that is about 10. So that will be 8000 into, is something wrong?
so we take 40 dB, then turn out to be
Hmm?
13.
Will this be? No, so that's about 10, but even this is too large. Where is the mistake? This figure is a bit on the higher side.
Bandwidth is 3.1 K.
Maybe 30 to 40 dB is a bit too large a value. For telephone channels, we have to check what is the signal noise ratio. It may be more of the order of 20 dB. I'll have to check now. I think I'm forgetting what is the signal noise ratio that we typically use in telephone channels. Suppose it is 20 dB, it will be 100, right? And 100 will be corresponding to
7.
7.
6.5.
And I think I'm also getting confused about this 2. Let me just check this. I'll have to check.
2B has to be there.
2B has to be there, but maybe there is a half here which I'm missing out. Yes, that's the problem. I'm sorry, there is a correction. This is half of this, so this becomes B times this. Let me rewrite this so that there is no confusion. For continuous channels, CS is half of log to 1 plus S by N, and C is B times log to 1 plus S by N in bits per second. And now our result for telephone channels will turn out to be 4000 into about what is
28,000 or 40,000.
more like what is the log of 100 to the base 2? 7. So about 28,000, 25 kilobits per second, right? So this is the typical figure that I am familiar with, and I was trying to cook to that figure, right? 25 kilobits per second for normal telephone channels. So that is what these most modern sophisticated modems, telephone modems, try to achieve, right? If somebody tells you that he has designed a modem which will give you a channel capacity or a data rate of information rate of 30,000 bits per second or 40,000 bits per second, you must know that he is making a fool of you, right? It is not possible. But the current state of the art is that there are modems which can go up to about 19.6 kilobits per second, right? And there are others which are in a fairly high state of development which take you very close to this limit. They are in the lab prototype stages. Okay, I think this is where we finish today. In the next two classes, that is on Friday and Monday,